All right. So let's begin, right? Okay, so hi everyone. I'm Ritojit Kundu. I'm a PhD student at IIT Kanpur, and today we'll be continuing with assignment two. So it is mostly about the content about week two, uh, and so this is the plan for this session. I'll start by giving you some hints about how to solve the assignments, and then we'll solve some problems which does not belong to the assignment but which are nevertheless important to strengthen your concepts. Okay, so let's have a look at this assignment. You can download this assignment from that course website. So let's look at this first question. So it says you that, okay, there is a state which is given as psi function of theta, uh, and they have asked you to calculate the density of states, the density matrix. Okay, so the density matrix, you know, that is given by just psi theta and psi theta. Okay, so you can plug this wave function psi theta, which is given in problem 1, and you can basically find this rho theta. Okay, so let me just check with everyone, is my audio clear, and is my screen visible to everyone? Right, okay, thank you. Okay, so you can from there onwards you can actually do this problem. This is pretty simple. uh, so so the next problem, in this problem 2, so now you're asked to calculate what is the commutation relation between Q and P. Okay, so Q and P are nothing but position and momentum operators. So in this particular case, you know that you can write your Q as a linear combination of A and A dagger, right? So Q is nothing but A plus A dagger divided by half divided by 2, and then P is again 1 by 2I A minus A dagger, right? So if you will use these two relations and you use the commutation relation of A dagger is equal to 1, so then you will be able to find out the Heisenberg uncertainty relation, right? So Q and P commutator bracket will give you IH cut. Okay, so do that. Okay, so and you will be able to answer this question as well. So let's look at the next questions. So which asks you to calculate the the equation of motions of these operators, right? So let's have a quick look at this, how one can do this. Let's just do this here. So this is my problem 3. So problem 3. So as you know from basic quantum mechanics, that the equation of motion of any operator, let's call it O. Okay, so any operator is given by this equation H comma OT. Okay, so this is called the Heisenberg's equation, Heisenberg's equation of motion. So what you need to do is, you know that the Hamiltonian is given in terms of this creation and annihilation operators like this, right? And so you are asked to calculate dA dt. Okay, so let me show you how to do this for this particular one, and you can do for the rest of other operators. Okay, so let's solve this problem. So now A is a function of t, right? And this is given by H comma AT. Okay, so let's have a look at how to calculate this commutator. So H is nothing but A dagger A plus half comma A. Okay, and there is a half A, this is a H bar omega. So H bar omega, because it's just a number, right? So I can get this out of this commutator bracket, and then we can simplify this commutator bracket even more, and which becomes nothing but this thing half comma A. Okay, so now remember the fact that commutator, any commutator with another operator is 0. So that's why this actually becomes 0. And then we are left with a dagger a, which is nothing but the number operator, and times h bar omega. Okay, and you know this commutation relation of n and a, which is nothing but minus a say h bar omega. Okay, so what we'll do is we'll plug this thing into this equation. So this is given by minus a h bar omega. So h bar and h bar cancels from here, so we're left with this equation. Okay, so let me write this thing clearly for you. This minus I a t omega. Okay, so can anybody tell me what is the solution of this differential equation? So anybody? That's right, that's right. So it will be just some constant. So the constant here is given by a0, okay, and e to the power minus I omega times t. Okay, so this is the time dependence of at. Okay, so now given that you know this this time dependence of at, you can also calculate a dagger. Okay, so how do you do that? So you just take the dagger of this expression on both of the sides, so it becomes a0 dagger e to the power I omega t. Okay, so this is how both of a and a dagger depends on time. So dependence is very simple. It is just a plane wave kind of dependence. Okay, so as you know the time dependence of a and a dagger, you can actually get time dependence of all other operator. Okay, so like x, so I'm writing in terms of dimensionless basis. Okay, so I'm not being too careful about the coefficients because I have absorbed them in my x and p. So x is given by a plus a dagger. So let me also mention this time dependence. So xt is given by 1 by 2 a t plus a dagger t. So now you plug these things back here. Okay, so these things and these things back here, so then you will be able to find out what is the time dependence of x. Okay, so similar thing actually goes for p also. So this is again a t minus a dagger t, and there is a I, right? Yeah, go on. Right. So like I mean this is not a number, right? So this is an operator, right? And if we, right, so this is an operator, and so let's look at this equation. Okay, so I am giving you that so I am giving you an equation which tells you a is equal to b. Okay, so now if I take conjugation in both of this left hand side and right hand side, what it becomes is a dagger is equal to b dagger. Okay, so whatever is on the right hand side, then you just take dagger of it. Okay, and these are not numbers, these are operators, so you will have to be a little bit more careful about this. So that's why I have written a dagger right here. Okay, or if you let's say you don't believe this result, okay, so what you can do is you can start again from this equation, but you just replace a by a dagger, right? So you in this Heisenberg's equation of motion, you replace a by a dagger and you do the same calculation. Okay, so you will see that finally you will find actually this equation. So you should do that, and this will also serve as a consistency check, right? So you don't have to believe me, you can directly do this, which is very simple. So I hope that is clear. So if you know, right, so if you know the time dependence of this creation and annihilation operators, you can basically find time dependence of any other operators. Okay, so this is basically what the next question asks. So so let's just take those down. So this we have done this. So we have written down this equation of motion for both of the annihilation and creation operators. And we also know this time dependencies, right? And you can plug those things to find out what are the time dependence of x and p as well. Okay, so I think that is fine. So at any point, if you have any confusions, you can unmute yourself and ask. Okay. Okay, so let's move on to the next question. So this is a very interesting question. So let's do the equation 5. So in equation 5, you are given the creation and annihilation operators in a different kind of notation. Okay, so in a different so these are in terms of number and phase variables. Okay, and from these operators, from these kind of definitions, you are asked to calculate the commutation relation between the number and the phase. Okay, so let's see how we can approach this equation. So okay, so this was my question 5. Okay, all right, so question 5. So now they have said that a is given by e to the power I theta square root n, and a dagger is given by square root n and e to the power minus I theta. Okay, I hope this is correct. Yeah, this is correct. So so the first principle, so what do we know about the commutation relations? So we know only one relation for this a and a, which is the most fundamental one. So this is just one, right? A and a dagger commutation gives you 1. So we can try to see if we message this equation a little bit, what do we get out of this equation. So now let's plug the a and a dagger from this equation. Okay, so now you can plug these things. So this becomes e to the power I theta square root n e to the power minus I theta minus square root n e to the power minus I theta and e to the power I theta square root n. Okay, so this is very easy. I am just substituting the relations which are given in the this question. Now what does this give me? This is nothing but e to the power I theta e to the minus I theta minus n is equal to 1. Okay, so I have done up to this. Okay, now what you can do, so let's for simplicity let's say that theta is delta theta. Okay, so delta theta is very small, so that we can ignore the delta theta square, so this is negligible. And so we can expand this exponential operators. So the first one becomes 1 plus I delta theta and n. Yeah, go on.
Sir, extremely sorry, I missed that part. Can you sir explain from
Right,
third line?
from the third line. Okay, so okay, so you're asking about this question. Okay, so basically, so let's start from here. So so we are given two different kind of representations of this creation and annihilation operator, and so now they are asking to calculate what is the commutation relation between the number and phase operator. Okay, so let's start from scratch. So we know only a fundamental relation between the creation and annihilation operator, which is just the commutator between correlation and this creation and annihilation operator is 1. Okay, so now I am just using this relation, and I am plugging in all of these things here. Okay, in that relation, and I am trying to see, okay, what do I come up with. Okay, so I am just getting this. Is this okay? I think my screen got stuck. Okay, so let me just try to join from here. Okay, it is a little bit delayed. Okay, so okay, now this is okay. So now I am just using these relations which are given in the question, and I am substituting them in the this expression, this one, and I am solving, and I have found up to this point. Okay, so now I am assuming that, okay, so let's take a very small theta. Okay, so that this delta theta square is actually negligible. It is very small, and we can just ignore it. So in that limit, we can expand this exponentials. Okay, we can expand these exponentials, and so this now becomes 1 plus I d theta. So the first operator becomes 1 plus I d theta, and then the second operator becomes 1 minus I delta theta. Okay, and there is additional n is equal to 1. Okay, so now I can just simplify this parenthesis. Okay, and so let's just do that. So this will give me n plus I delta theta n minus I n delta theta, and there will be additionally a delta theta square term, but which we are ignoring for now. Okay, so so from this actually some things cancel, so this n and this n actually cancels, and we get this expression that I a commutator of delta theta comma n is equal to identity. So we are almost there. So just a few more steps. Delta theta n is equal to minus I, so I have taken the I onto the other side, and so we can actually use the commutators. We can just flip the commutator, right, to get an additional minus. So n comma delta theta is equal to identity. Okay, so now you can ask me, okay, I am doing this for a very small theta. Now how do I ensure for a general theta? So you can actually show it for a general theta. Okay, you can show it for a general theta, that what you will get is n comma theta is nothing but identity. Okay, so because this is the operator equation, and this will hold for any kind of any powers of theta. Okay, so you can try to prove that. So I'll be doing only up to here. So this is what it will give you the commutation relation. Okay, so is this okay? Right. Okay, so let's see see about the other problems. So we have done the problem 5 as well, and so there are other things like, so okay, so the 6, so it is actually quite well done in the video. Okay, if you look at the video of coherent states, so there Professor Saurabh Basu actually explains very well how to calculate this ANs. So I'll not be doing that. So I'll rather encourage you to look at the video to complete this problem. Okay, so okay, so reference, let me write as reference to video. So there are other things. So this other question is about this displacement operator. So the displacement operator, similarly, so this kind of thing. So if you will use the inner product formulas of this coherent states, then you'll be able to do it very easily. Okay, so all of these questions, like the last 3 questions, so this is also done in the video, and this other is definitely done in the video. So I'd encourage you to refer back to the video to solve these problems. Okay, so I'll not be doing these problems, so rather I'll be doing something different, which might be interesting to some of you. So let me just tell you about what I'll be doing for the rest of the session. So we'll have a deep look at the commutators of 2 operators. Okay, what happens for finite dimension and what happens for infinite dimensional operators. So you will see that a very bizarre thing happens for infinite dimensional operators. Okay, so so secondly, we'll have a look at a potential well which is actually infinite in one direction and quadratic in the other direction. Okay, we'll see that what are the states for this kind of harmonic oscillator. So we'll then have a look at a charged harmonic oscillator. That means that my particle in this harmonic this half m omega square x square well, this has a charge. Okay, this has a charge q, and if I am adding another electric field, then how does the states look and how does the states change? How do I calculate them? Okay, then after those things I'll be doing some problems about coherent states. So firstly we'll prove the completeness relation of coherent states. Okay, and then we'll try to understand the coherent states in a little bit more detail. So we'll get the coordinate space representation of psi alpha x of this coherent state. We'll look how the coherent states depends on time, and we'll look how this x average in the coherent state that looks like. Okay, so we'll see that very interesting properties. So this coherent state very interesting properties, and I hope you will like them. So let's first start with this first problem. So let me copy it into some free space. All right. Okay, so what does the question says? So we know that trace of a comma b commutator is actually 0. So how do you show this? So commutator of a comma B is nothing but AB minus BA. Alright, so now if I take the trace of this operator A comma B, so then what do I get? So trace of AB minus BA. Okay, so trace is actually linear kind of operator, so I can break this apart into this combinations of AB and BA. And trace has a very nice property that you can change the operators cyclically. Okay, so like I can change this to be A B. Okay, so I can change this like cyclically I can change the operators. Okay, so now you can clearly see that this actually cancels and gives you 0. This actually cancels and gives you 0. Okay, so now so this is kind of a eyeballing thing. So you can eyeball on some operators and you can get some of the properties from just looking at the trace. Okay, so for example, so let's have a look at the angular momentum states, rather angular momentum operators. So angular momentum operators, so let's write one of the commutation relations. So Lx comma Ly will give you I Lz. So this kind of a thing. Okay. So okay, so I am doing in dimensionless unit, so I am not being too much careful about h bars. Okay. So but let's say, so let's look at this thing, like let's take a trace on both of the sides. Okay. So trace of Lx comma Ly. And then there is also trace on the right hand side, trace of Lz. Okay, so we know that trace actually vanishes. Okay, so this is 0. Trace of this commutator actually vanishes. Okay, so because I have just proved to you that trace just vanishes. But on the other side, so then that implies that trace of Lz is nothing but 0. Okay, so we don't know how the Lz operator looks like. Okay, but what we know that but trace of this operator is 0. Okay, so that is like eyeballing, that is like eyeballing check. Okay, so like somebody gives you a angular momentum operator. Okay, and you write in a matrix form. Okay, you write in a proper basis, and you can directly just calculate the trace. Okay, calculate the trace of that matrix, and you can directly say whether it is a viable angular momentum operator or it isn't. Okay, just before checking all of the commutation relation, you just first go for the this trace relation. Okay, so in this case the trace of Lz operators will be 0. Okay, and you can also show that trace of all other operators, like trace of all other angular momentum operators like Lx is also 0. Okay, and trace of Ly is also 0. So like using other two commutation relations, you'll be able to see that. Okay, now we are convinced that the trace actually gives you trace of a commutator gives you 0, right? So so these three properties should hold for all of this angular momentum operators, because they are coming from a very fundamental commutation relation. Okay, so is this point clear, or anybody has any confusion about this about this statement? So please ask. Okay. Okay, I hope this is okay. But now if you are convinced that okay, trace of a commutation is actually 0, now let me puzzle you a little bit. Okay, so let's have a look at this commutator x comma p. Okay, so you all know that this is I h bar. Okay, and if you are talking in terms of matrices, so this is just identity. So let's say I have some representation of x operator in a matrix form, like you know that how to write these operators. Okay, so let me just recap this x. How do you write this? So x is nothing but half of a plus a dagger. Okay, so let's forget about this h bar now. Okay, so let's say that h bar is 1. Okay, so let's look at the physics of how this thing how does this thing look like. Okay, so a in a matrix notation, it looks something like this. So there is a matrix. Okay, and so the dimension is not mentioned, so dimension is very large. Okay, dimension is of this matrix is very large, and it is 1 square root 2 square root 3 square root 4 dot dot and so on and so forth. Okay, and all other entries are actually 0. And similarly, a dagger operator looks similar kind of thing, but this all of the numbers are on the other side. So 1 square root 2 square root 3 square root 4 and so on and so forth, all of the other terms are actually 0. Okay, so when you compute these kind of operators, then actually there is no upper bound to this dimension. Okay, so basically all of these matrices are infinite cross infinite dimension. Okay, so there is no bound to all of these matrices, and so you can actually use this expression of x. Okay, you can use expression of x, and you can try to calculate this x operator, okay, and the p operator, and you calculate the commutation. Okay, so you multiply all of these matrices and you just calculate the commutation. So when you will do that, you will then let's say you take the trace. Okay, you take the trace of this thing, and we know that from our previous discussion that that the commutator's trace should be 0, right? Commutator of two operator and that trace should be 0. But we know that this is nothing but I h bar identity. Okay, so this is I h bar identity, but whose trace is not 0. Certainly it is not 0, right? So actually the statement I made before, that the commutation trace of a commutator is 0, is not valid for infinite dimensional matrices. Okay, so this is a very simple argument to show you that the operators like x and p in case of harmonic oscillator, that becomes an infinite cross infinite dimensional matrix. Okay, and the commutators trace might not be 0 as well in that case when operators are infinite dimensional. But you can always look at finite dimensional operators, and you can get out some simple properties like this, which you have enumerated, right? So yeah, this is a little bit puzzling, but yeah. So is this okay, or some doubt? Please ask me. Okay, so is this okay? Yeah, go on. Yeah, obviously you will get this. So these are recorded, and yeah, you'll get it. Okay, so is this okay? Is this problem okay? So do you get the point that for infinite dimensional operators, the trace of the commutator might not be 0 as well? Okay, all right, so this is just to give you a little bit of puzzle. So let's look at some other problems. All right, okay, so let's have a look at this problem. So we have a half harmonic oscillator. Okay, so I'll show you what do I mean by that. Okay, so we have a half harmonic oscillator. Okay, so what does that mean? So that means that one of the direction is actually goes as half kx square, and the other direction is actually 0. Okay, so now we want to solve so we want to find the states and the energies for this this system. Okay, so anybody has some idea that how should we proceed to get the states and the energies? So any idea? Right. Right, right. Yeah, so the step you mentioned, we can start from the Schrodinger equation, and we can actually solve from the scratch. Okay, but we can be a little smart here, and we just think a little bit like physicists. So we don't want to start from scratch. Rather, we want to use the information that we have. Okay, so what information do we have? So we know that for a full harmonic oscillator, which goes as half kx square, so we know the energies, right? So the energy is given by n plus half h bar omega. Okay, and the states are, so you know the states. So states are Gaussian type of things. So it can be, so these are basically Hermite functions, Hermite polynomials. Okay, so you know the states. So how does the ground state look like? So ground state is just a Gaussian kind of thing. Okay, and so first excited state looks something like a odd function. Okay, so it's just the odd function. Okay, so you will notice that all the odd all the this let's say odd states have nodes at x is equal to 0. Okay, and all of the even states there is no node for x is equal to 0. Okay, so now in this problem, in the given problem, we see that there is a hard wall. Okay, so at the whenever there is hard wall, then there should always be a node. Okay, so there can be some kind of wave function, but the node should always be there. Okay, because the potential actually diverge, potential becomes infinite at that point, so psi must go to 0. So we can actually, so I mean, just to give you the answer, so all of the states that you know from this harmonic oscillator, okay, so you can just take the odd states, okay, which has a node at x is equal to 0. Okay, so what do I mean by that? So odd states, so let me write it down. Odd states, so odd states means that the En is given by 2n plus 1 plus half. Okay, so 2n plus 1 is an odd number, right? And the states will be all of the odd states. So let me write a psi tilde n is nothing but, so psi x 2n plus 1. So this is your old harmonic oscillator states, full. And this is your half harmonic oscillator states. So you can actually take this equation and you can plug back into the Schrodinger equation and try to see whether this states satisfy the equation or not, the Schrodinger equation or not. Okay, so like we are being very smart here, and we are not starting from scratch, and we are identifying that there should always be a node at x is equal to 0, because the potential is infinite at that point, and we are using that information, and we are trying to look at the whole spectrum of the eigenstate of the full harmonic oscillator, and we are finding out which states are becoming 0 at the x is equal to 0. Okay, and we see that only the odd states are 0 at this x is equal to 0, and this must be the solutions of the Schrodinger equation of this half harmonic oscillator. Okay, so this is very simple. Okay, so as simple as that. Okay, so is this argument clear, or you need a better clarification at that? Is this clear? Right. Okay, so let's move on to the next one. All right. So okay, so I just missed a part. So given that you know all of the states, you can actually find out what is the x square average. Okay, so I'll leave that for you. You just take the odd solution of the full harmonic oscillator, and you plug into x square in those expectation values. Okay, and you will be able to get this all of these things. Okay, all of this x square average. So you can calculate it at ground state also. Okay, so now let's look at another. Okay, so why do you think it will be 0? Okay, so let's have a discussion about that. Yeah. Okay. Okay, so yeah, that's quite nice that you're thinking like that, but it is not that simple actually. So okay, so when does the odd or even function, this definition comes up? Okay, so odd or even definition is only there if the function exists on both side of x. Okay, so this is positive x, this is minus x. Okay, so I can say, okay, this is an even function, and this is an odd function. Okay, but this argument actually doesn't hold if I have only some function here. Okay, I do not, so if I just reflect it, so where will it go? It will go somewhere here. Okay, so if, because my wave functions are only here, right, so this will be my ground state of this case. So my wave function is only on one side, because on the other side it is infinity. Okay, so so there is no parity, so there is no evenness or oddness in this case. All right. So x square will not be 0. X square in all of the case, in all of the case, it cannot be 0. Okay. So why it cannot be 0? Because you see x square is related with this. So x square average minus x average square is your sigma x. Okay, is your delta x. Okay. And Heisenberg's uncertainty principle will prevent you from making these things 0. So x square average for a symmetric case also it will not be 0. Okay, and here it will be not 0 because there is no parity in the system. Okay, you can just argue from that. Okay, so is that clear? All right. So yeah, so let's move on to the next one. So okay, not this one. Yeah, so this is another interesting problem. All right. Okay. Okay, so now okay, so so how we did this harmonic oscillator was, so okay, there is a particle in the harmonic oscillator which has a mass m. Okay. Okay, so now I am telling you that okay, it additionally has a charge. Okay, it has also a charge, so charge is given by q. Okay, and I am saying that okay, if I am applying a electric field in this direction, so this is a 1D problem. Okay, this is a one dimensional problem, and my electric field is given by E I cap. Okay, so now I am asking you, for this quantum mechanics problem, can you find the solutions? Okay, and again you can start, obviously you can start from scratch, you can start from basic principle, but you want to be a little bit smarter. Okay, so first of all, let's see that let's try to find out what is the energy, because of what is the change in energy in the Hamiltonian. Okay, because of this electric field. Okay, so the information is electric field is given by EI. Okay, so 1D, I don't have to write I also, but just to make this absolutely clear, so this is in x direction. Okay, so this is the electric field is in x direction. So the potential, you can actually find the potential is nothing but E dot dx in this case. Okay, so so the potential is so this is just nothing. E is a constant, it doesn't depend on x, so this is just E times x. Okay, so the work done is nothing but q times v. Okay, so it is, I mean, the energy, the total energy is q times v, so this thing becomes q E times x. Okay, so this is the additional term in your Hamiltonian. So let's write this the total Hamiltonian. Okay, so h was given by half. So let me write it like p square by 2m. Okay, so I'm not being very careful about writing hats, but you should be, I mean, I am emphasizing this, that all of these are operators. Okay, these are not functions, these are operators. So p square by 2m, and there is half m omega square x square, and additionally there is a QEX. Okay, QEX. So this is because of applied electric field. Okay, so now I want to find what are the energies and what is the wave function of this problem. Okay, so can anybody try to approach this? I mean, how one should approach this problem, how one should try to solve it? Any idea? Anybody, from anybody? Yeah, 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 that's right. So yeah, so we can make it a complete square. Okay, so let's try to do that. So p square by 2m plus half m omega square. So I am taking the m omega square part out, so this is x square minus q e x by m omega square times 2. Okay, so I can so now to complete the rest of the this whole square, so I need an additional q e by m omega square whole square and minus q e by m omega square whole square. Okay, so now we can actually complete the square. So it will become x minus q e by m omega square whole square, and there is this additional negative term which is half m omega square q e by m omega square whole square. So I can actually cancel one power of this, and so the final Hamiltonian is nothing but p square by 2m plus half m omega square x minus, so let me call this quantity x naught because that is just a constant. Okay, minus q e square by m omega square, and there is a half. Okay, so so how does this look like? Okay, so this looks like we have a harmonic oscillator which is a little bit shifted. Okay, so let me define another variable so that you can identify a little bit better. So okay, so let me just write x naught is my q e by m omega square, and so let's define a x tilde operator which is x minus x naught. X tilde minus half q e square by m omega square. Okay, so I mean we are doing a formal change of variables. Yeah, go on.
Sir, it will be x tilde square.
X tilde square, right? Yeah, I missed that. So we are doing a formal change of variable. Okay, so now let me write this p, also p tilde. So p tilde is our I h bar del x tilde. Okay, so in this kind of coordinate system, so we basically know the solution of this part of Hamiltonian, and there is a constant term. Okay, so if you add any constant term in your Hamiltonian, that doesn't change your eigenvalues, that just shifts them. Okay, so we know what is the energies of this thing. So energies are just the normal energies of a harmonic oscillator. Okay, so this is given by n plus half h bar omega. Okay, but this is not complete yet because there is additional this constant term. We have to take account of that also. So this is n plus half h bar omega minus half q e square by m omega square. Okay, so this is the energies of the this harmonic oscillator, where the particle is charged and I have an additional electric field in the x direction. Okay, so these are the energies. Now what about the states? So psi n, so let me write it as psi n tilde. Psi n tilde is the states. Okay, so psi n tilde, this is also a function of tilde. Okay, so now this is nothing but your psi n x minus x naught. So all of your solutions, so all of these Gaussian kind of solutions, all of these Hermite polynomials will be now shifted to x naught. Okay, so yeah, so this is just take the solutions of a harmonic oscillator and shift it by x naught. The states of harmonic and shift by x naught. Okay, so let's try to have a look at this. How does this thing look like? So we have potential well. Okay, and there is a additional electric field in the x direction. Okay, so what happens is this actually gives you a just x proportional to x terms. So your this potential is not at zero anymore. It is actually little bit shifted, and it has a minus energy also. Now let me call this part as your x0. Okay, and this is my minus half q e whole square by m omega square. Okay, so this is basically, you have now a shifted harmonic oscillator, and the solution is pretty simple. Okay, so is this clear, or you want me to repeat something? Okay, so I hope this is clear. Yeah, right. So you see all of the energies. So you see in the Hamiltonian, so there is this minus quantity is sitting, minus a constant term is sitting here.
Then why it is the right side of the
Uh, uh, why it is in the right side? uh, oh, okay. Oh, okay. So okay, so now let's try to think a little bit about the Quadrian transformations. So now in this problem, what happens is, so my new origin is x naught. Okay, so you see that if my x is equal to be x naught, has to be plus x naught, right? Then only there is this minima is there. Okay, or you can actually take this expression. You can actually take this expression, and you, let's say all of these things are just normal numbers. These are the functions. Then you can try to find the minima, where the minima is. So you will see that the minima is currently shifted at x is equal to plus x naught. So that's, so you see, yeah, right? So when this x will be plus x naught, then our origin, so this is the new origin of the modified problem. Okay, so okay, so any other questions? Okay, so let's move on to the next one. So if you have any comment also, you can just know me. Okay, or is this too fast, is this too slow? You can just know me that also. So let's have a look at the coherent states. Okay, so we'll look about some properties of coherent states. Okay, so in the lecture, in the video lectures, the professor actually asked that you can also calculate this completeness relation. So this coherent states are not orthogonal because their overlap is not I mean, it is not orthogonal, right? So you can see from that the overlap of the overlap of this different coherent states are not zero. Okay, so in literature it is sometimes called as overcomplete states, so overcomplete basis. But these, even if they are not orthogonal, they still span a basis. Okay, so if they span a basis, then there exists a completeness relation for these also. So let's have a look at these completeness relations. So what we want to do is, we want to calculate this quantity. So we want to calculate this quantity. Okay, so we want to find out, okay, what this is. Okay, so this is actually the completeness relation what we are trying to derive, and the lambda here is a complex number. Okay, so as you know that coherent states, so if you just look at the property of coherent states, so A acting on a coherent state lambda is that gives you lambda times this thing, right? So lambda is generally a complex number, so it belongs to the complex numbers. So that's why there is this integration is over the whole complex plane. So that's why I have written a d2 lambda, right? So d2 lambda means the whole integration over the complex plane. So and we'll use this expression. So like how these coordinate states are expanded in terms of this number states, we'll use this property and we'll try to proceed. Okay, so let's just use this relation and let's insert it here. So this is d2 lambda, and then there is a summation over n. So I'm inserting the first identity. So this is lambda to the power n by square root of n factorial, and there is n. Okay, so this is my one of the insertions. So another insertion will be so I have to take a different dummy variable, right? Because otherwise this summation indices will mess up. So m, so lambda to the power m by m factorial, and then there is this m. Okay, and this is lambda star to the power m. Okay, so I have inserted these relations. Okay, and let's try to simplify this a little bit further. So this is d2 lambda. So there is a summation over n and m, and this n and m, this actually goes from 0 to infinity. Okay, if this is not clear, this goes from 0 to infinity. So over all of the harmonic oscillator states. So this is lambda to the power n and lambda star to the power m. There is a denominator n factorial square root m factorial, and there is n and m outer product. Okay, so you want to basically solve this problem, Now so there is a nice trick. So we can actually go to polar coordinate. Okay, so sometimes to do the complex integrations we can go to polar coordinates. So let's say that my lambda is given by r cos r e to the power I theta. Okay, so this is like a polar representation of any complex number. Okay, so this is generally, so all complex number we can write in terms of a radius times some phase e to the power I theta. Okay, so let's use that here. And so what does that, so if you do this change of variable formally, so this will become r dr d theta. Okay, so you have to calculate the Jacobian, or you don't have to think about this. So this is the measure, I mean the thing you need to insert to do the integration, or in the polar coordinate. Okay, so now I'll write, so let me just keep the summation summations out in m is equal to 0 to infinity. So there is r dr and d theta. So lambdas I'll just insert here, r to the power n e to the power I theta n, and then again r to the power m e to the power minus I theta m, and there is this denominator in factorial by m factorial. Okay, so let's try to simplify this even more. So n comma m is equal to 0 to infinity, then there is r dr, and r to the power n. So let me just write all of the r's together, r to the power n plus m plus 1, and there is this theta integral d theta e to the power I theta n minus m. Okay, where theta goes from 0 to 2 pi and r goes from 0 to infinity, because we have to cover the whole complex plane, right? And there is additionally this denominators m factorial. Okay, so now let's have a close look at this this thing. Now you see that this is just sines and cosines. Okay, so what happens when you integrate a sine cosine over the full period? Okay, so because the sine cosines have the positive and negative part, this actually cancels over the full period. Okay, but when this will be non-zero, so this will be non-zero when when n is equal to m. So when n becomes equal to m, then there is no phase basically. Okay, so then you just get just 2 pi. Okay, so how do we write this condition in a compact manner? So this we write like 2 pi delta m comma n. Okay, so this is the result of this integration. Okay, so we'll be using this, so let's just use this result. So n comma m is 0 to infinity, so there is integration 0 to infinity dr r to the power n plus m plus 1 and additionally there is also 2 pi and delta m comma n. Okay, so now actually, so this is a Kronecker delta. Okay, so Kronecker delta, so let me write the definition of Kronecker delta so that this is absolutely clear. So this is 1 if m is equal to n, and this is 0 if m not is equal to n. Okay, so if you use this property, then you can actually sum over any one of the variables. Okay, I have missed this factorials, n factorial, m factorial. So let's sum over m. Okay, so if you sum over m, then there is only one term. When m is equal to n, that term actually contributes to the summation because of the Kronecker delta. So now this becomes, so now the summation is only from 0 to infinity, and there is r integration which we are yet to do. So r to the power n is equal to m, so we just write it to n plus 1. Okay, and there is our 2 pi, and there is 1 by n factorial. Okay, okay, so now we have to do this integration, right? So now if you are familiar with the gamma functions, okay, so I'll just give you the identity. So the gamma function, so this integration is this gives you a gamma function. Okay, so what do I mean? I'll just write. So this integration 2 times, let's say dx, so x to the power 2t minus 1 and e to the power e to the power oh, I have missed some e to the powers actually. Yeah, I have missed those e to the powers. Yeah, so I have missed this. Okay, so let me just write this e to the power minus lambda mod square. So, okay, so because there will be two of these, so I'll just use lambda mod square. So yeah, so lambda, so e to the power minus lambda mod square. So there is, so when I'll be substituting this lambda is equal to r e to the I theta, so it will just become e to the minus r square. Okay, so then e to the minus r square and e to the power minus r square and e to the minus r square as well. Okay, so minus t square is minus x square. Okay, so now if you compute this thing where this integration goes from 0 to infinity, so this will give you a gamma function, gamma to a gamma of t. Okay, so gamma of t is given by t minus 1 factorial. Okay, so this is just a factorial. This is a fancy way to calculate the factorial. This will give you the factorial function. So I'll use that result. So n is equal to 0 to infinity, and yeah, I am missing some terms also. So there is this additional n comma m outer product. So there is additional n comma m outer product, n comma m outer product, n comma m outer product. Yeah, so now we get so if you just use this standard integral, so you will get a gamma n plus 1. Okay, so gamma n plus 1 times 2 pi 1 by n factorial e to the minus r square. Okay, I am also missing something, or no, I am not missing anything more. Okay, so what is gamma n plus 1? So like I just mentioned, gamma n plus 1 is just gamma n factorial. Okay,
Sir, the outer product will be there, right?
yeah, sorry for being so much clumsy. Yeah, so the outer product, so n factorial, so there is another 1 by n factorial, there is a pi, and there is okay, there is no other this e to the minus r square, there is only the outer product. Okay, so you see this actually cancels, this n factorial and this n factorial cancels, and what do you get? So we get pi times n 0 to infinity summation n. Okay, so we know that this is just the completeness relation, right? So this is just 1. Okay, so let's use that. So then it becomes just pi. Okay, so after doing this, all of this algebra, okay, all of this algebra, so what this boils down is d2 lambda is nothing but pi. Okay, so basically if we just take the pi here, so this becomes 1. Okay, so this is basically the completeness relation obeyed by the this coherent states. All right, so yeah, I can understand that this derivation is actually a little bit long and you have to sit through to do this whole thing, but is this okay? Because so later on basically you will have these notes, you know, also have this video of this session, so that you can have a look back to these calculations. Okay, so is this clear, or if you have any questions, please ask me. Okay, okay, all right. So yeah, coherent states calculation, sometimes it can become a little long, but nevertheless, so let's look at the last problem. So last problem has several parts, but this will give you the physical picture of coherent states. Okay, so this is important. Okay, all right. So okay, so we know about the coherent state, right? So what is the coherent state? So like any alpha, coherent states is written in terms of minus e to the power alpha mod square by 2, and there is a summation over n e to the power so lambda to the power n by n factorial n. So is a factorial okay? Okay, so there should be a square root. Okay, so this is the expression for the coherent state. Okay, so now we are asking that what is the coordinate space representation of this this state. So what we want to do is we just want to take a x. Okay, so we just want to project the state onto x, so that we know the representation in position this coordinate space. Okay, So then it becomes nothing but this. So x actually grows through all of these numbers. So then x directly acts on this n. Okay, and we know that x comma n, this gives you the solution of harmonic oscillator, which we call as psi n x. Okay, so this is basically our this coordinate space representation. So this is nothing, so let's denote it by psi alpha x. Okay, so psi alpha x is a linear combination with some particular so these are like, so if you calculate the probability, this transmission probability, you will see that these coefficients are nothing but Poisson distributions. Okay, so this is the coordinate space representation of these coherent states. Okay, so now we can actually look at the time dependence of these coherent states. Okay, so we want to find out what psi alpha xt looks like. Okay, so again, to do that, what we'll do is we'll attack this state with the this Hamiltonian, right? Psi alpha x comma 0. Okay, so let's try to do that. So it becomes so e to the power I h t by h bar, and I have to act this operator on minus alpha mod square by 2 lambda to the power n by n factorial square root and psi n x. Okay, so the e to the power I h t, this is because of this is a linear operator, this will go through all of these numbers. Okay, and it will directly act on the state. So it will directly act on the state h t bar psi n x. Okay, and it will directly, what it will do is it will inject the time dependence, okay, into that state. So let me write that down. So I can directly use n plus half h bar omega. Okay, so there is also t, so there is okay, so h bar will be cancelled from okay, so I hope this is clear. And then what I can do is I can actually get out I can actually get this minus I omega t part out, and then I am left with lambda and e to the power minus I omega t to the power n by n factorial psi n x. Okay, so you see that what I am doing here. So I am trying to put this time dependence inside the this eigenvalue. Okay, so let's write it like that. So this is minus I omega t e to the power minus alpha mod square by 2 summation over n, then lambda as a function of t n factorial psi n t. Okay, so we'll see that why this is useful. So so now the eigenvalue this eigenvalue in this eigenvalue equation of annihilation operators, this becomes actually time dependent. So lambda t is lambda e to the power minus I omega t. Okay, so this is we can again write this thing as psi, so alpha t and x. Okay, so like we are using the time independent equation, but now the time dependence has been injected inside the alpha itself. Okay, so I am mixing up the lambda and alphas. Okay, so actually it should be, all of these things should be alpha. Alpha, so this is alpha t alpha. Okay, so my psi alpha x comma t has this kind of time dependence. So is this clear, or so is this clear to everyone? So all of the time dependence is inside the alpha now. Okay, so this is how the coherent states actually depend on time. Okay, so the next question is what is the x average? Okay, so what is the x average if I take alpha x alpha? So okay, so before that let me just say that what is the average in this state. So any answer, what is the expectation value of x in this state? right? So because this is just by the symmetry of this harmonic oscillator, if you're looking at the eigenstate of the harmonic oscillator, then this is nothing but 0. Okay, but what is this? Will it be 0? So any hint what it can be? Will it be 0? So actually it will not be 0. Okay, so we can try to solve this thing, but so let's also put the time dependence. Okay, so we want to measure the expectation value of x as a function of time. Okay, so what happens is, now, so let's use the x's definition in terms of the creation and annihilation operators. So this is 1/2 alpha t, then a plus a dagger, then alpha t. Okay, so we know that so a actually acts on alpha t, and it will give you alpha t times alpha t. Okay, so you can actually take a sandwich from the other side also, alpha t. Okay, so then this will just be alpha t. Okay, so similarly for the other a dagger, similar calculation will give you alpha star t. Okay, so now let's put all of this thing together. So this is alpha t plus alpha t star. Okay, so now we can actually write this thing as real part of alpha t, right? So whenever there is a complex number plus is conjugate, so you can basically write it as a real part. Okay, so 2 times real part basically, so the half actually cancels. Okay, so again I'm using the dimensionless units, so I am not being too much careful about some h omegas around here. So again you can put all of these things together and this will still be true. Okay, you're just looking at the physics. Okay, so real part of alpha. So what does real part of alpha is? So this is alpha is given by alpha times e to the power I omega t, rather minus I omega t. Okay, so real part of this thing is given by alpha cos omega t. Okay, so this is just alpha cos omega t. Okay, so what does this actually physically mean? Okay, let's try to visualize a little bit. Okay, so let's say this is your particle in the harmonic oscillator. Okay, and you have given some kind of states. Okay, some sort of a state. Okay, and so I have showed you that as a function of time, its expectation value, it's x average. It means x average will be here, right? So x average at t0 will be here. So this actually changes back and forth. Okay, changes back and forth. So it is just like you have a well and a particle is bouncing on the walls. Okay, so that's how this coherent state is bouncing back and forth through the well. Okay, so actually this coherent state has only this kind of property. If you will take any other linear combination over the number states, over the harmonic oscillator states, you will see that it will not maintain its shape. It will disperse away. It will not be localized on some point. But it is like a classical thing, right? It is like a classical ball which is bouncing around. Okay, so this actually shows you the expectation value, I mean, which just tells where the wave function is. Okay, the wave function is actually going back and forth. Okay, it is doing this kind of motion inside that harmonic oscillator. So this is a very nice way to visualize what is the coherent state and how does it look like. Okay, so that is so is this okay, or is this okay? So please, can anybody tell me, is this okay? Is is there any confusion? Okay, so yeah, this is really nice. So this is just like a classical thing in quantum mechanics, right? So just a ball which is bouncing back and forth in frequency omega. So this omega is the frequency of your harmonic oscillator. Okay, so if you know any kind of programming languages, let's say Mathematica or Python, you can try to animate it. Okay, you can try to animate this whole wave function, and you will see that okay, this is actually going back and forth. That will be pretty nice. Okay, so yeah, I think that is the last of the question that I was trying to do for this session. Yeah, so actually I'm finished with the session now. So if you have any additional question, you can please ask me, okay? Or you can also post in the forum which is there, and any of the group members will try to answer your question. So is this clear? Anybody has any question?
Thank you, sir. It was such a nice session.
Okay, okay. Thanks, Himanshu.
I'm a third year undergraduate student.
Okay.
Thank you, sir. I'm quite unfamiliar with few things. So, sir, I think by what's being good and clearing the basics, so I think
Right.
I will be familiar with this.
Right. Yeah. So you have to sit down and you have to focus on this thing for a little bit. So it is actually not that much hard. It is quite simple when you understand the basics. It is quite very simple. Okay. So yeah. So thanks for joining the session, and I hope you have a nice weekend. Okay. I'll see you next week. Okay.
Thank you, sir. Thank you so much.
Yeah. Thanks everyone, and have a good weekend. Okay. So I'll see you next week. Bye then.